This is our last lecture discussing MATLAB, and after this we'll dive right into the finite difference time domain method. In previous courses where I taught computational methods, in fact, the topic of this lecture is not something I taught. I really thought it was, or I assumed it was obvious. We have a two-dimensional array, maybe we set it all to zeros, and we set a certain set of pixels in the shape of a triangle, for example, and then we could model scattering of a wave around the triangle. And I went on and taught the method, and everybody understood that. And it turns out everybody got bogged down putting these geometries onto the data arrays so that we could simulate different devices. So that was a mistake I made, and now there's an entire lecture devoted solely to how do you put a geometry into a data array that then your algorithm would start number crunching and modeling waves, scattering, diffracting around whatever you've put onto that array. So first we'll talk about MATLAB data and arrays, how to initialize them. And in this class, we, for the most part, will not be doing three-dimensional modeling. We'll talk about it off and on. So we need to understand how a three-dimensional model, because we live in a three-dimensional world, everything really is three-dimensional. What does it mean when we talk about a two-dimensional and one-dimensional model? And in fact, what you'll see is even if we're doing a one-dimensional finite difference time domain code, in fact, we're modeling something that is three-dimensional. And so to understand that relation, I think, is very important. After that, the meat of the lecture is really discussing how we add the geometry of what you want to model to the array so that we can model it. Arrays. So this is just a one-dimensional string of numbers stored in MATLAB. And they really come in two different flavors. We have what we'll call row vectors, where we store 1, 2, 3, 4, 5, in this case, in a row. So it's a horizontal array of numbers. And in linear algebra world, whether something's a row vector or a column vector actually can make a difference. A column vector is still, it's a linear array of numbers that we store in memory. However, they're vertical, 1, 2, 3, 4, 5. So we create row vectors by separating numbers by commas. We can create column vectors by separating the numbers by semicolons. So how do we create a row vector? How would we use it? Well, we create a row vector. One way is use a linspace command, or linear space. And this will create a string of numbers that starts at -1, ends at 1, and there'll be 100 different numbers in that array. So we'll always create something like this every time we want to plot graphics, and that will be our horizontal axis, the positions of all the points along the horizontal axis. But given these arrays, we can do some really neat things. We can just say y equals x squared, and notice we're doing dot caret squared. The dot caret does a point-by-point squaring. It just goes to each element in x and squares it. So now y is another linear array calculated from x, but it's x squared. And so then we would just say plot x comma y, and out would come a graph something like this. So row vectors is more graphics oriented, if you will, although it does pop up in linear algebra from time to time. Column vectors is really exclusively a linear algebra concept. We use this when we're doing matrix algebra. We'll have some big ugly square matrix, we'll multiply a column vector, and we'll get another column vector. But in the end, both of these are just a linear array of numbers. It's more just geometrically, are they a row or a column, and that has implications in how we use it, whether it's in linear algebra, whether we pre-multiply or post-multiply certain things. So be sure you know the difference between row and column vectors, because sometimes you can run into troubles if MATLAB wants a column vector for a certain operation and you give it a row vector. It'll give you an error, something like inconsistent matrix size or something like that. 2D arrays. Well, here we're making a 2D array. It's a 1, 2, 3, 4, 5, 6, 7, 8, 9. Now in memory, this is still stored as a linear array of numbers, and we'll talk about that later on in the course. But we could separate the 1, the 2, and the 3 by commas, because this is a row of numbers. The semicolon takes us down to the next row, 4, 5, 6. Semicolon, we're down to the third row, 7, 8, 9. And so we can create an array like this. And of course, we already know we can use the command imagesc to give us the values in that array. We see we have a 3 by 3 array, and each color has a certain value associated with it. And we can use the color bar command to give us a little legend here of what color corresponds to what number. And we talked about this last time too. How do we visualize 1D arrays? We use commands like plot. Another one that's very common in digital signal processing is the stem command. And you'll notice these two are the same functions, just two different ways of visualizing it. Also, you'll notice there's ugly white space over here. We could have done another command here that would be an axis tight, and that would get rid of this ugly white space. "2D arrays are the big two in my mind are image SC and P color. Notice the difference here. A is still a 3x3 array. Image SC shows us 3x3 numbers. P color is showing us 2x2. Well, what on earth is happening here? Well, in fact, there are 3x3 numbers here. However, they just occur at the bounds. So you can imagine one number happening along these left edges, the second number at this interface, and the third number over here, and it's interpolating the colors in between. Whereas with image SC, the numbers really are in the middle of each of these squares, which is really why when I'm doing my troubleshooting and day-to-day activities in MATLAB, I like to use image SC because it more directly shows me the data in the arrays that I'm working with, whereas P color, not so much. It's really interpolating the colors between the numbers. There's two main ways that I use to create linear arrays of numbers. There's the linspace command, and then there's more just creating a direct sequence. My preferred way is the bottom, the direct array. But let's look at linspace. Linspace, again, has three input arguments: the start number, the end number, and then how many numbers you want in the array. So if we say 0, 10, in 10 steps, notice what these numbers look like. 0, 1.11, 2.22, 3.33. And you'll notice that the data does not really conform exactly one per unit cell. They're offset a little bit, and it's very easy if we have a grid that we want to model something on that's 10 by 10. They usually would be much larger. If we create our axis arrays with linspace, something like this could happen where we're accidentally telling our algorithm the position of those points is not exactly where we intended it. If we do what I call a direct array now, we still want 10 numbers. We want the step between them to be exactly 1. Now we can say, let's go from 0 to the number of points minus 1 and then multiply by the step size. Now we have an array that goes 0, 1, 2, 3, 4, 5, 6, all the way up to 9, and those conform exactly to the unit cells. So when I create grids for finite difference time domain or other methods using a grid like this, I always use a technique like this to create the axis array XA. I rarely ever use this linspace command simply because it's much harder to control the positions of those points. It's very easy to trip up and not do this correctly. Whereas down here, it's much easier to get everything consistent and correct. Now we need to talk about what it means when we model something in 2 dimensions or 1 dimension, because we live in a 3-dimensional world, and no matter what we're doing in our model, we are modeling a 3-dimensional device. So let's try to understand that a bit more. Point number 1, all physical devices are 3-dimensional. In certain circumstances, we can make some approximations that let us model a 3-dimensional device as either a 2-dimensional or 1-dimensional system. First, why would we even want to model something in 2 dimensions or 1 dimensions when everything really is 3 dimensions? Why not just build a 3-dimensional model and be happy with that? So let's think about a typical 3-dimensional grid. And this 20 by 20 by 100 looks large, but in fact it's on the smaller side. To model a real device, we probably need more like 40 by 40 by 200. But let's just say we have 20 by 20 by 100. We probably could model something realistic on this grid. So the total number of points in this grid is 40,000. 20 times 20 times 100, that's 40,000. So if we were going to do a finite difference time domain analysis, the size of a three-dimensional array is about 3.5 megabytes. Well, for each point in the grid, we have 6 field components, E and H, each with an XYZ component. We also have different material values, and in the end, we have about 12 different numbers that we need to store for each point. So now we're up to about 240,000 numbers that we need to store. So the size of a single 3D array is about 42 megabytes. In these days, that's not such a big deal. As I mentioned, this is a pretty small grid. It can get much larger. But the point is, pretty soon we're storing gigabytes of memory, and it becomes much more computationally efficient if it's possible to bring it down to 2 or 1 dimensions, because we have orders of magnitude less memory, and it's much, much, much faster. Now, here's a neat thing. Doing a time domain analysis, and this really is a key benefit of finite difference time domain, to store this grid, it only takes about, let's say, 50 megabytes. And this is a time domain analysis. If we were to do the same thing in the frequency domain, where we are building matrices, the matrix that we would need to build is about 120,000 by 120,000 complex numbers. That is a total of 14.4 billion complex numbers that we would need to store and process to represent whatever's on this grid. So complex numbers have a real and an imaginary part, so we're really talking about almost 30 billion real numbers that we have to store. That's about 215 gigabytes. So we're starting to approach a terabyte of memory. Now, it turns out the matrices associated with this are mostly zeros, and it does not make sense to store those as zeros. We instead store what's called a sparse matrix, where we ignore the zeros and only store the non-zero elements. When we do that, this drops down to about 8.2 megabytes just to store the problem. We haven't tried solving it. When we do solve it with a direct method like an LU decomposition, our matrix ends up being about half full, and this would take about 110 gigabytes to solve. So in finite difference time domain, for this same problem, we need 50 megabytes. To do the same analysis in the frequency domain, we need 110 gigabytes. So we've done 2 things here. We've shown that 3D problems lead to large arrays, large memory, slow simulations. But even still, the time domain analysis that we're learning this semester is a whole lot more efficient for large problems than doing a frequency domain analysis, because frequency domain analysis involves matrices and linear algebra, and everything seems to scale exponentially. Now we're going to take what is really a 3-dimensional device and show you how we can reduce that down to just a 2-dimensional simulation. Let's say we have something here that looks like a ruled diffraction grating, and we'll have to assume that in this z direction it's infinite extent. And also you'll notice that it's uniform in this z direction. Nothing changes. Well, if nothing changes, any derivative in that direction will be 0, and that's where Maxwell's equations begin to simplify. But we have this infinitely extruded dimension. If we look in the other direction, kind of going across the bumps of the grating, we'll also assume this goes to infinity, that this just keeps repeating and repeating and repeating out to infinity. But in the z direction, that's not the case. So we have probably air, we have our grating, we have a substrate, and then maybe air beneath that, or maybe the substrate even kind of goes off to infinity. What we can do is wrap a little box around one of these unit cells. And we call it a unit cell because we can take this and stack it onto itself from left to right and reconstruct the 3-dimensional device. So what we come away with is a 2-dimensional grid where we have the air on the top, we have our grating tooth, and our substrate. And later on we'll discover that we can use periodic boundary conditions on the left and the right, and that makes it look infinitely periodic going left to right. On the top and the bottom, we will use absorbing boundary conditions, so any waves scattered from this will hit these boundary conditions, just get absorbed and disappear, and they won't reflect back into the problem. So we really can represent a 3-dimensional device on a 2-dimensional grid, and this is much more efficient to analyze on a 2-dimensional grid. But this is still just a picture of our device. Then we move over to our grid, and notice we have to fill in all the different material properties. So up here we probably have a refractive index of 1 because it's air. Down here we're saying the refractive index of our substrate is 2. And in the tooth region we're saying the refractive index there is 3. So our whole goal to describe our device is to build a two-dimensional array that has numbers placed in it like this, such that if we plotted this to the screen, we would see our device. And the whole purpose of this lecture really is to discuss how to build these things. Another way we can go from a three-dimensional problem to a two-dimensional problem is with some approximations. And let's say we have this crazy integrated optical circuit here, and there's some kind of rib waveguide happening, and it splits once and then it splits twice, and we have 4 outputs. This is a three-dimensional problem and actually very computationally intensive to model something like this. What we can do is we can look at a cross-section away from the waveguide and basically average the refractive index here and calculate some kind of effective refractive index away from the waveguide. We can also look at the cross-section through the waveguide and calculate some other sort of average or effective refractive index. That'll be a little bit bigger than N2. Given these two effective refractive indices, we can sort of look straight down on top of this circuit and construct a two-dimensional array this way, built from these two average refractive indices. Now we've taken our three-dimensional device and built a two-dimensional model from it, which is a whole lot more computationally efficient to do. And this actually is a very, very accurate way of doing things. This is called the effective index method. And finally, we can go from 3 dimensions to 1 dimensions. And when we start off learning finite difference time domain, we will be learning about one-dimensional analysis. And what does that mean? So imagine we have these slabs of dielectric. These slabs are assumed to continue off to infinity in the transverse direction. So here I'm kind of showing in and out of the board. Also of infinite extent in the up and down direction. But in the direction of the wave, these are finite slabs. So we can describe any number of slabs, but they're infinite extent in these two transverse directions. We can represent this three-dimensional device on just a one-dimensional grid. And notice we're filling this one-dimensional grid. We have air out here, and then we're filling in the material properties of our slabs, and then we have air again. And so this is a one-dimensional array that we would build in our MATLAB program that then we would run our simulation on. But even though it's a one-dimensional array, it really is still representing a three-dimensional object. And it's very important to understand the connection there. Sometimes we can take a very complex three-dimensional device and still represent it as a one-dimensional problem. So let's look over here. We have a bunch of different slabs with arrays of holes of various sizes. This is very complex. This would be a rather intense three-dimensional analysis. If we look at this, we say that has really big holes. It probably has a lower overall refractive index. We would make it a uniform slab of low refractive index. This has little small holes. It's mostly the dielectric, so it probably has a higher refractive index. And essentially we're taking averages through all of these different layers. We can now represent it as a stack of homogeneous layers, if you will, and we can assume they're of infinite extent in the transverse direction and build a one-dimensional array that would describe that. Now this works really well if the holes are much smaller than a wavelength, and so the wave really just sees an average. If the wavelength approaches the size of these holes, that wave will begin to diffract and it splits in different directions and a whole bunch of other complicated stuff happens. This is not good for modeling that type of a system, but if these holes are really, really, really tiny, we can just take averages and still model that as one dimension. And it is always good practice to do this. We're simplifying the computations in our models by taking what is truly a three-dimensional device and either modeling it as 2 dimensions or 1 dimension. So it is always very good practice to do that. On to the meat of this lecture, where we discuss how do we actually get these different geometries on data arrays. Things like circles and squares and triangles. How do we position them? How do we size them? How do we do all this? First thing we'd always want to do is initialize arrays. And we already talked a little bit about this last time, but let's say we want an array that's 10 by 10. And if we want to initialize it all to zeros, we would just use the command zeros. And then we tell it the size of our grid, nx by ny, or 10 by 10 in this case. Maybe we want to initialize it all to ones, and we just use the command ones. So usually I start off initializing to zeros. It's rare I would initialize to ones. What I normally do for me is I make everything zeros, I put ones where I want a material to be, and then once I build all that, at the very end I convert that over to real material properties like refractive index or dielectric constant in one easy line of code that I'll show you at the end of this lecture. The next step, how do we put geometries in this array? Well, step one, always initialize, so I'll initialize to 0. Let's say I want to put a circle in this. I like to use meshgrid for this, but I'll start off, I'll create 2-axis arrays. This tells me the positions of each point in the x direction. Notice I'm using linspace. We're going to break away from this soon because when we're doing grids like this, it's trickier to get the positions right using the linspace command. But anyway, we have our x-axis, we have our y-axis. At that point, we'll call this meshgrid command, and that will create two-dimensional arrays, x and y. The big X will have all of the positions, all of the X positions of each point in the array, and the big Y will be all of the Y positions of each point. Once we have these two from meshgrid, that lets us very easily type just one line of code to make rather complex shapes. In this case, we can visualize this. That's the equation for a circle. And so if we say A equals all points where x squared plus y squared is less than or equal to 0.75, we're making a circle in the middle of this grid. Another theme you can start to see here is that looks very blocky to be a circle. So if we added more and more points to this grid, rather than being 10 by 10, if it was 100 by 100, we would see something that looks much more like a circle. However, it should also be rather obvious that a 10 by 10 array will model much faster, whereas the 100 by 100 will model much slower. Maybe more accurate, but will model slower. So when we're modeling, we're always battling this. How coarse of a grid can we get away with so we have fast simulations, but we're also still accurate? Now this is something peculiar that I do, and causes a lot of confusion, but in fact I think there'd be much more confusion if we didn't do it this way. So I guess I'd say the way I do it is horrible. It's just better than anything else I've tried. But here's the problem. MATLAB, the title MATLAB is actually, it stands for Matrix Laboratory. If you create a variable in memory, MATLAB assumes that's a matrix and that you're going to do linear algebra with it. Now remember how matrices are referenced. If we have element A sub mn, m is the row number, n is the column number. So in other words, the first number you give it is how far down you are in the array. The second number you give it is how far horizontally you are. So if we say a mn, the first number is how far up and down in the array you are, and the second number is how far left and right you are. Now this is a problem for me. Again, going back to where I think the students that I've taught have the most trouble is building the geometries on the arrays. We think x comma y. We want that first number to be our horizontal position in the array and the second number to be our vertical position. However, MATLAB says, no, we're working on a matrix. That first number is how far down and the second number is how far over. And so things are backwards. So recognizing really the bulk of the confusion is building the array, I turn that around and I say I'm going to make that first number be the horizontal position and the second number be the vertical position. Now we can build devices much more intuitively, and really the only time we run into troubles there is when we visualize, because when it's visualized we use ImageSC, it thinks it's visualizing a matrix, so we just have to tweak those commands when we visualize. But I think it makes the building of stuff much more intuitive. So when I'm building a device, I think this way. A is nx, ny. So nx being the index position horizontally and the index position vertically. I don't think this way, AMN. This is assuming matrices. So we're flipping it around now, and that has consequences when we visualize things. First thing, we need to revise how we use meshgrid. If you type help meshgrid, out comes code that looks much like this, where we do an x comma y. But we're flipping things, where now our y is what MATLAB thinks is x. So in fact, we will use meshgrid this way. We still create our x-axis and y-axis the same, but when we call meshgrid, we will swap x and y. So I don't think we'll ever use meshgrid this way. I only use it a couple times in this lecture as an example before I started discussing what we're doing here. So we'll use it this way. We also now need to revise our plot commands. Now that we're building everything with a swapped sense of dimensions, we used to be saying image SC, X, Y, and then A, but since A we're building rotated 90 degrees, if you will, we will use an image SC, our x-axis, our y-axis, but then A prime. And notice the prime is actually the complex transpose, but since image SC only lets us plot real valued things anyway, the complex conjugate of a real number is still just that real number, so I just use a single quote, although technically I probably should be using a dot or a period apostrophe. Okay, so we initialize A all to zeros. We'll stick a 1 in position 2, 3. MATLAB assumes, oh, this is a matrix. We want to be 2 positions down and 3 positions over. So 1 position, 2 position, vertically, so we know we'll be in the second row, and we're going to be in the third column. 1, 2, 3. So here's our 1. However, when we're building geometries, we would like this to be 2 over and 3 down. So A apostrophe or A transpose, 2 over, 3 down. That's where the 1 is placed. And so we do it this way because it's more intuitive when you build it, and there's just a few places where we need to do things a little bit differently when we visualize and build meshgrid. But otherwise, we can build things in our traditional sense of X and Y. Okay, technique number 1. Very often we model things as rectangles, things like ruled gratings, diffraction gratings. There's just a lot of stuff that have square features. They're easy to build, they come up a lot, they're easy to model, so we want to be able to put rectangles into our array. I always do it this way. If there's ever a rectangle that I want to put in an array, I calculate 4 numbers. I calculate the starting index, I'll call nx1, so notice that's the 1, 2, 3rd column over. So I calculate the start and stop indices in the x direction, and I also calculate the start and stop indices in the y direction. Once I do that, I can just fill in that rectangle. So watch how this happens. We will initialize A, our 10 by 10 array, all to zeros. Then we define our start and stop indices, just how we're showing over to the left, and then in one command we fill in the rectangle. We say we want to fill in A from nx1 up to nx2, and from ny1 up to ny2, and we'll set all of those to 1s. So this little section of code creates this array with that rectangle sitting in there. It's even more common to center a rectangle. So here's a full snippet of code which illustrates my entire thought process from the beginning of how I would do that. The first thing I like to do is define the physical size of the grid. So that's SX and SY, the physical size of the grid. This is the thing that's in meters or centimeters or whatever units you're working in. The next thing I'll define is the size of the grid in terms of the number of cells. So I want to represent something that's physically sized, let's say 1 meter by 1 meter, with 10 by 10 cells. The next thing I'll do is I'll define the size of the rectangle. In the x direction it's only 0.2, so it's a fifth of the total width, and in the y direction it'll be 0.6. So notice it is skinny in the x direction and tall in the y direction, so it's consistent with wx and wy. Well, I'm still going to fill in the rectangle the same way. I want to calculate the start and stop indices for both the x direction and the y direction, the start index and the stop index. Where are those in a way that centers it? The first thing we need to do is calculate the cell width. So this little dx is the width of one of these cells. So it's the total physical width divided by the number of cells. That makes sense. The next thing I want to do is calculate how many cells wide this rectangle is. So that's this calculation. We take the physical width, we divide it by the width of the cells, and then we'll round that to an integer. So this tells us, in terms of an integer, how many cells wide that is. We're not free here to fill in half of a cell. If we needed to do that, we would just have to use twice as many cells. So we have to round that to an integer. This must be an integer. So nx is how many cells wide the rectangle is. Then we want to calculate its start index. So what we do is we'll take nx, big NX, that's the total number of cells, divided by 2. That gives us the center of the grid. And we'll subtract from that the number of cells wide the rectangle is, also divided by 2. So it's kind of like we're starting at the center, and then we subtract half the number of cells. And of course we want to round that to an integer. Floor rounds down. And then we add 1 because MATLAB starts with array index 1 instead of array index 0 like most other codes do, like C. So that's our start index. Once we know that, our stop index is simple. It's our start index plus the number of cells wide our rectangle is minus 1. This minus 1 is actually pretty important. If we didn't put that here, we would be one cell off. For example, right here we have little nx is 2 cells wide. So we would start in 1, 2, 3, 4, 5. So nx1 will be 5. If we said 5 plus 2, without putting this minus 1 here, we would have a 7. And if we fill that in, we actually would have filled in 3 cells, 5, 6, and 7. But it's not, it's only 2 cells wide, so we have to subtract 1 for our stop index. And then the y direction, we're doing the exact same thing we did above. First we calculate the cell height, which is the physical height of the grid divided by the number of cells. Then we calculate how many cells tall the rectangle is, which is the physical height of the rectangle divided by the cell height, and we're rounding. And then we calculate the start index vertically, and we're using the same algorithm for centering, and then the stop index. Once we have all that, we can initialize A to zeros and then fill in our rectangle. So this group of code creates this centered rectangle, and the centering algorithm I use all the time. It comes up a lot. Okay, our next geometry. Now we're experts at rectangles. What about circles? Very often electromagnetic things are circles or cylinders or something like that. So we're doing a very similar procedure here. We define the physical size of the grid, how many cells we want our grid to be, and now we're going to use meshgrid to do circles. Rectangles we can get away with just start and stop indices, but circles I think it's easier to use the meshgrid command. So we're going to need these axis arrays to do that. But we still calculate the cell width the same way, physical width of the grid divided by the number of cells. We're not going to use linspace here. And we create an array that goes 0 up to the number of cells minus 1, and then we'll multiply this by the grid resolution. So this will tell us the left position of all of the cells in our grid. And for doing this circle, I like to center things. So I'll take this axis array and divide by the average value, and that centers it. We'll do the same exact thing for the y-axis, calculate the height of the cell, create our y-axis array, and then center it around 0. Now we want to create a circle. Let's say we want the radius of that circle to be 0.4. We'll create our mesh grid. Notice we're reversing x and y here, and then we create x. And here's the equation for a circle. That's why meshgrid's so cool, is because we literally can just type in the equation for a circle, and it does that. Big X and big Y are two 2D arrays the same size as this. The big X array contains the X positions at each point, and Y contains the Y positions at each point. So we literally just say anywhere where x squared plus y squared is less than or equal to little r squared, will set to 1. Everything else will be a 0. And that's exactly what comes out of this. So suddenly we can make circles. And so the only difference in code really is creating these axes that we use for meshgrid, and we're constructing a circle this way. So we're not using start and stop indices or anything like that anymore. We're using meshgrid. Okay, well, circles are kind of boring. What if I wanted an ellipse? How do we do that? We actually have two different radiuses or radii now. But the start of the code all stays the same. We're still defining the physical size of the grid, how many cells we want. Now instead of 10 by 10, we're going to 20 by 20. We create our axis arrays exactly the same, and we're still going to use mesh grid. But now we have two different radiuses. Notice the radius in X is a little bit smaller than the radius in Y. And we see that here. This ellipse is a little bit skinnier in X than it is in Y. So the modification comes to what was our equation for a circle. And now instead of having our r squared here, we essentially move that r squared and divided x and y by that. But that gives us an opportunity to assign different numbers. And that's exactly what we do. We say x over the x radius squared plus y over the y radius squared. And any place here that's less than or equal to 1 will set to a 1. Everything else is 0. And so out comes an ellipse with our two different radii. Okay, suppose we want an ellipse, but we also don't want it centered. How do we do that? Well, we start off exactly the same way. Physical size of the grid, how many cells we want in our grid. We create our grid arrays, we center them, we still center it. So X, Y, A, and YA will both be 0 right around the center of our grid. The difference is in how we're creating the ellipse. We need to define more numbers here. What is the center position in X? What is the center position in Y? And what are the two radiuses that we want? We create our mesh grid. We're still swapping X and Y in the mesh grid. And so the big change is in how we do this. So we take our big X and we subtract the center position. And then that difference we divide by the radius. And then that whole ratio we square. And we do the same thing for Y. It's Y minus the center position. Put parentheses around that, divide by the radius, put parentheses around that, square it, and then anything less than or equal to 1. And now that creates an ellipse with center here in the X position negative 0.15 and in the Y position positive 0.25. And we notice that the radius in X is about 0.4. So this distance is about 0.4. And this distance, the radius in Y, is about 0.2. So now we can create circles that are no longer circles, they're ellipses, and we can place it anywhere within the array. We can also do something like this. For lack of a better word, I call it a formed half space, where somehow we define some function, defining a line, and we want to fill in all of the values either below it or above it, either way. So we define our grid the same way we've been doing, physical size, number of cells, our axis vectors. And then here we define the line. So this is just a line somewhere in XY space. We're going to use this to fill in ones below that line. So here's the code to do that. We'll initialize A to all zeros. Then we go into our for loop. So we're working from left to right here. So we're going 1, 2, 3. Little nx is going 1, 2, 3, 4, 5, all the way across the grid. For each point, we want to calculate the y index of the top of this curve. So let's say we're at this third point. We want to calculate ny, that position. So that's what this code is doing. We're going from the middle of the grid. We're going up by that function value. That's our physical height. We divide by the cell height and round it, and that gives us the number of cells. And then we just simply fill it in. We're at position nx. And we'll fill in all the numbers from 1 to little ny and set those all to 1s. And that'll fill in everything below the line. And so we do a for loop that goes all the way across. And we've now filled in half of our grid with some arbitrary function. Now we're going to do something a little bit more sophisticated. Let's say we have a line cutting through the middle of our grid somehow, and we want to fill in one side of that line but not the other in some simple way using meshgrid. We don't want to have to set up a big for loop and go through all the points and check each individual one. So how can we do this? Let's look at the math just describing a line. So in the lower left here we have a line, and 2 points can define a line. So the input to this little algorithm is just the position of 2 points, an x1 and a y1, and an x2 and a y2. Well, given 2 points, we can write the equation for a line this way. So x and y are our positions. Y sub I and x sub I is just, we pick either one of these points. Either one will work. And then we calculate the slope, rise over run. So that's just y2 minus y1 divided by x2 over x1. But the point that we put in this equation could be either 1 or 2. Doesn't matter. We can just pick one. So that's the equation of a line that comes out of knowing 2 points. So we'll take this equation for a line and rearrange it a little bit. We'll set it equal to 0. Well, now we can locate one half or the other. If this equation is greater than 0, we're talking about all of the points that are to the upper right of this line. If we look at the same equation but less than 0, we're talking about all the points that are below the line. And of course, all of these where it's equal to 0, that is exactly on the line. So we can locate either half, the upper or lower half, by looking at this equation for a line. If it's greater than 0, that's everything to the upper right of the line. Less than 0, everything to the lower left. So let's think about how we can do this in MATLAB now to fill in half of our grid in some arbitrary way. So here's our grid, and we're picking, again, 2 arbitrary points, x1 and y1. So the top half of our code is the same. We have the physical size, we have the number of points, we have our 2 axis arrays, but now we're going to do a mesh grid command. We're still swapping x and y here. And now here's where we fill in the half space. We define the position of our 2 points. So we have x1 and y1, x2 and y2. And then it's simple to fill in the half space. The first thing we need to do is calculate the slope, but then we simply say, hey, anywhere where big Y minus Y1 minus M times big X minus X1, remember that's just the equation for the line, anywhere that is greater than 0, we want to fill in. So remember, that fills in the upper right. So suddenly all of these become 1s and everything else stays 0s. If we had said less than 0 here, we would have filled in the lower left. And so you can also imagine doing this in combinations now to make things like triangles and hexagons and other things. So that's where what we call masking and Boolean operations. We know how to make rectangles, we know how to make ellipses, we know how to fill in half the grid either under a function or above or below some kind of arbitrary line. So these are sort of our primitive geometries. Well, it turns out we can combine these to make pretty complex things. Think about making a house. A house is a triangle sitting on top of a rectangle. And maybe you'd put a door in there by removing a rectangle. So imagine creating separate grids. So for example, we have our formed half space. We also have our linear half space. And we could Boolean these together. And suddenly we see this line for our linear half space, but then where this line would continue down, where now our formed half space is taking over. So we end up with something that's a little bit a hybrid of the two. And so learning how to combine these things, we can very quickly, very easily make some pretty complex geometries. And this is really all there is to it. Anything that I do on grids is really just combinations of everything in this lecture. The final last thing, we'll have this grid now that's just 0s and 1s. In finite difference time domain, we need an array that has the permittivity, the material properties across space. Well, a permittivity of 0 is not possible. This doesn't make sense. We just use 0s and 1s for convenience so we could build geometries and do Boolean operations on them. Our last step is really to convert this over to realistic values. So let's just say we built this, we have some circle that we like, and really we want the dielectric constant out here in these white regions to be 1 because that's air, and we want the dielectric constant of our object to be 2.4. Well, there's 2 ways we can do this. We don't need to do both of these lines. I'm just showing you 2 different ways that we can do it. We can say 1 minus a. That will essentially make these outer regions black, and the inner region's white, or these outer regions 1s, and the inner region 0, and we can multiply that by ER1. So in other words, we will have a bunch of ER1s out here and zeros within the circle. Then we go over here, we use just A and multiply by ER2. That puts a bunch of ER2s out here and zeros still out here. So when we add these together, we'll get our overall grid where we have all 2.4s inside this circle and 1.0s on the outside. Another way we can do it is just put ER1s everywhere. So now there's 1s everywhere. But we want to put 2.4s in here. We don't just want to add this dielectric constant to it because we'd end up with 3.4 in here. So what we add to it is ER2 minus ER1 times A. And that will also create this grid. So either one of these will create the same thing. We don't need both. They both do the same thing, just two different logical ways of ending up at the same place. So that's it. We now know how to put different primitive geometries on a grid. I talked a little bit about Boolean operations, how we can combine them to make more complicated things. And then the final step is converting those over to realistic material properties where we're doing something like this. And that concludes this lecture.